Well, I practice a lot of integration religions, and one of them is data, and it's been north of 20 years now, though I don't like to admit that too often. So we get asked a lot about what's the difference between Firebolt and Snowflake or Redshift, and the questions go on and on and on. So we decided we better have a session about this. In fact, we got the question so many times, and we saw what folks like Fivetran had been doing with their benchmarks. So we decided we better release something and get some information out there. So today we're going to spend some time talking about that, about not just what the comparisons look like from our perspective, because we're a little biased, we're a vendor, but how should you think about comparing the latest cloud data warehouses or query engines or everything else that's out there, and how should you do your own evaluation. So we're going to spend a little bit of time on that. And I think the first thing to remember is the history. That's partly because I've seen a lot of it. But there's an old Agatha Christie novel, Elephants Can Remember. And we probably should too. We should remember Hadoop, that imaginary friend of Cutler's Kid from way back when. It rose to popularity in part because of the need for speed. What happened was Teradata and a couple other data warehouses, as they were hitting deployments with about a petabyte a decade ago, the performance was going down because the data was soaring. There were new kinds of data that were being loaded in, and it was causing the data warehouses to hit some hard limits. So in came Hadoop. People started trying to offload the ELT, the raw data they were loading into Teradata, and the transformations back into the pipeline. And Cloudera and others started coming in and helping with that. And then came data lakes, and then came trying to do interactive analytics on top of data lakes, and Presto popped up after Hive popped up. And then it didn't work so well. If there's one thing we should remember about that history, is if you try to throw brute force, inefficient, elastic scale at interactive analytics and think that elastic scale is going to improve the performance on top of unstructured data, you're going to have a problem, because we tried and failed in that last round. And now in some ways we're there again. We're trying the same thing again. So if you remember nothing else, remember that history repeats itself. And I do too a couple times. So what we thought we'd do is we'd explain what evaluation criteria seem to come up and why. Why is it that people pick the half dozen or so categories that we're going to go through today? Then go through the comparison, give you 30 plus different criteria that you can think about, along with the evidence behind it. Because the evidence is out there. You can go dig, and through documentation, through various boards, and find the right comments that help you understand the pluses and the minuses, some of the limitations of the different technologies. So we're going to go through that so that you can at least see for yourself why some of these criteria might matter for you and what the evidence is behind it. And then you can go through the comparison guide that we released, and tomorrow I think you're going to send out a link during the conversation, and we'll send out a link after to make sure that you have it. Because as I said, I'm a little biased. I'm from a vendor here, so want to make sure that by the end of this conversation, you get a sense of how to use the criteria that are here for your purposes, and how to think about the evaluation, a POC, a benchmark that's a little bit more objective or really biased for your needs, not for ours. Okay. I think we want to start with a survey. We often do. So it's funny, this is pretty close to what we see usually. About 3/4 of the audience, this is the amalgamation of all the surveys. About 3/4 of the audience say they're either focused on customer facing or both customer and internal facing analytics. Of those, a good half of them are using Snowflake or Redshift. The Snowflake numbers were higher here The Redshift was a little smaller. The BigQuery was a little bigger. But it's order of magnitude about half of the folks already using a data warehouse. And the majority, give or take, right around half, usually say it's not just scale or speed or cost, it's all of the above that are the challenges we're facing right now. So that this, the mix here we have on the call, on the webinar right now is about what we see normally. And it shouldn't be a surprise that it's not uncommon, because there's a lot of data out there that points to the fact that speed and scale, or really speed and cost at scale, are a problem. And I mentioned the Fivetran folks before. They've been doing a benchmark for about 3 years now, just looking at how Snowflake and Redshift and BigQuery and Presto, which is kind of like a proxy for Athena, since Athena is a commercialized version of Presto effectively, how they perform. And they're all in about the same ballpark. If you test them out on a terabyte of data with a big fact table, a 4 billion row fact table, one user, one query at a time, just running a first time query, Fivetran found that it takes you about 8 to 11 seconds across all of them to run that query on average. And some queries go into the minutes. And that's not fast. If you need to do interactive analytics, that's too slow. That's okay for reporting. It's okay for some dashboards where you're not waiting, but first time queries, if you're waiting on them, that's way too slow. And the costs aren't low either. The prices they used were about $16 an hour and $8 for Presto, since Presto's open source. So you're talking just about the infrastructure. So at that price, $16 is about $150,000 a year if you're going 24/7. The more business critical, mission critical editions like Snowflake Business Critical is going to be twice that. So it's going to be approaching $300,000 a year. So clearly, speed and cost and scale are concerns. And so they should be in the criteria. Remember, this is only a benchmark for a terabyte. Imagine some of the bigger deployments getting up to hundreds of terabytes or a petabyte, how they would perform and what the costs would be there. So these are 3 criteria that pretty much have to be in there. How do you trade off performance, scalability, and cost, and where do you land? Now, the reason we're hitting these and the reason we're having these conversations, the survey that you answered and the results we usually see, 3/4 of the people have gone beyond reporting and analytics. They're getting into operational analytics. That could be watching network performance or telemetry, security monitoring, service monitoring for customers, supply chain, monitoring e-commerce, shopping cart experience, IoT, so devices and machines as a service or in a shop floor. All of that is operational, and we see a lot of use cases for getting analytics out to employees to support these kinds of projects. And then, of course, there's delivering analytics to end customers. Part of it is delivering a service like ad tech, watching your ad performance, which every marketing department at this point uses. But part of it can also be a SaaS offering. You want someone else to monitor your security for you as a service, or do network telemetry for you. The ad tech vendors are all like that, right? They are offering this as a service for your ads. And as you're doing reporting and dashboards, you'll get into some cases where scale is a problem. The data's gotten so big that you're running into having to figure out how to scale better. But generally, by the time you're deploying out to employees or deploying out to customers, speed becomes a problem. It has to be a second or less every time. It has to be fast. And if you're going beyond an analyst team of maybe 100, 200 people in a bigger company, and you're going to thousands of employees, and then you're going to tens or hundreds of thousands of customers, cost becomes an issue too, because you can't keep spending $1,000 or hundreds of dollars a user to support this kind of infrastructure. It just end up being too much. What that says is use cases matter too. You have to, by use case, figure out what are the key capabilities you need and how is that going to impact cost and performance and scale as well. And then, since a lot of us are architects, architecture matters too. If you look at the changes that have happened from the on-premises data warehouses, which had a lot of good techniques, there's a lot of lessons learned still from the Teradata's and Verticas and Parexels and the Tezas of the day. You watch the evolution. Each generation had something different in their architecture that had its pluses and minuses. Redshift ported Parexel. They ported an on-premises data warehouse into the cloud. They made it like a managed data warehouse service, but it simplified deployment and it simplified some administration as well. But it is the most traditional of the data warehouses out there. You spin up a data warehouse. You can read replicas of the master write data warehouse to scale out horizontally, but it's still one data warehouse for the data. It's not really decoupled storage and compute the way we think about it with what happened with Snowflake and BigQuery and Athena. When they introduced decoupled storage and compute, they really separated compute. Any engine, any node, any cluster can be attached to any number of data stores. So it really made it truly decoupled. Now, that simplified administration more. That also, the decoupled storage and compute made it possible to do any kind of elastic scale for compute and for scaling users out horizontally. But it still didn't deal with speed and with cost. And we'll go into that. And that's where Firebolt and some other third generation technology started to fill in the gap. And along the way, if there's one thing we realized, to get that speed and scale required a rework. It required some architectural changes. Now, if you've seen the benchmarks before, the changes do matter. When we do a demo and we run against a larger data set, what's an ad tech data set, it's 20 times the size with 10 times the number of rows. It's a wider table. And we're still able to get 1 to 2 second performance, depending on the type of query you're running. So using a data warehouse that a cluster that fully loaded all the costs in are 1/3 to 1/6 of the cost, depending on what edition you're using in the traditional cloud data warehouses. So maybe for, at 1/6 of the cost, for 10 to 20 times the scale, you can be 7 times faster, or a few orders of magnitude better in price performance. That matters, but that takes a lot of architectural change. So the final set of criteria is, what do you need out of the architecture? What needs to be in the architecture to get the speed, scale, and costs that you're looking for? This is what went into our thinking. And it's what should go into your thinking. When we get asked, okay, well, how do I evaluate these different data warehouses? Really, how do you compare? What's the difference? It's on those dimensions where you try to figure out the difference and what it means to you. And you shouldn't just do a comparison. You need to do the benchmark. You need to do a POC and test it out for your particular use cases. You need to do that work. But we started at least by releasing this comparison guide and doing the comparison. On the right-hand side, you'll see a long list. This is actually just the summary table. This is not the detailed table. There are over 30 categories that the guide goes through, and you can look at some of the details in there and in the write-up on what people typically find across the different data warehouses and query engines. The link's at the bottom. Tamar's going to send it. But what I wanted to do is walk through the categories and give you a little bit of a flavor of what's important, what's not, and how to think about it. So I'll start with the following pieces of advice. First, think about your use cases first. Lay out your roadmap like any good architect. Lay out your roadmap for the projects you need to do and what you need to adopt when, because that'll give you your features, your key features you need now that you need for the first projects. It'll help you understand what you might want to wait for. But you need your roadmap to understand how to evaluate this technology. You can't just pick a technology for the current project and then paint yourself into a corner and realize you can't use it for the future projects. You need to look ahead a little bit. Think about your criteria that matter to you in these projects, because not all these criteria are going to matter for you, and they're going to be weighted differently. You're going to put a different priority on some of them. So lay that out too. Think about the evidence you need. Prove it for yourself. Pull the evidence from here, pull the evidence from other places. Do your own benchmarks, because there are lies, there are more lies, and then there are benchmarks. And they're very tailored and very specific to whatever someone was running the benchmark against. And you need to run the benchmark for you. So get ready to do that and to do your own POC. And then the final piece, I'd say, because the mindset's changed a little bit, and I hear it in architects that I talk to. I remember one saying, you know, it's a lot easier to switch now. And the truth behind that statement is, in some ways, the data pipeline has become the data. As we've been building these new pipelines for data lakes and then switching from data lakes to specialized engines like a data warehouse, we've gotten used to the reality that we're going to have a few different data warehouses or analytics engines. And as an architect, if you need to accept something like that, that you might have to get a new engine, you need to design for it. So design for change, that's what we do, right? Design for the reality that you're probably going to have to move your data into something new over time for different projects. Design for multiple engines. And so that means designing your pipeline to be able to support that. So with that said, let's start going into the categories and what's going to make the difference for you. Let's start with architecture. That's where every good architect should start. So starting with what isn't different. Most of these cloud data warehouses now use decoupled storage and compute. It's a good thing. It's a great design. It shouldn't really be changed. The difference is going to be in the details and how the decoupled storage and compute works. Redshift has added RE3, so you can dynamically provision and spin up and spin down a cluster. But understand the one thing that you still can't really do, you can't have multiple databases attached to any different engine and it just works. It's not 100% decoupled. And understand why you'd want something like that. Why do you want an ELT engine and a query engine working against the same data? Why do you want different engines for different workloads working against the same data? It matters. So you want to think about your use cases, but the fact that there's decoupled storage and compute is probably not going to sway your decision. General AWS integration and what you integrate to, what the technology supports in AWS probably isn't going to make the difference, but you should make sure you have your checklist of, you know, do I need to, you know, support some kind of integration with a third-party AWS technology or AWS technology? Make sure you have your checklist of all your integrations. I don't think data and network security is going to make a difference. In my own personal experience, doing a little bit of a teardown and understanding, you know, how's the role-based access control work? What kind of, you know, SSL termination does it support? How does the firewall work? How do you, you know, control access into the VPC? That stuff is pretty similar. Amazon does a reasonable job of looking at the vendors and giving them advice too. So I don't think that's going to make a difference. I think the certifications for regulatory requirements will. What is different is, first, isolated tenancy. The Redshift probably has the most flexibility here. You can run Redshift on your own VPC as well. Snowflake didn't. allow that until they had virtual private Snowflake. And there it's the Snowflake sub-account, an isolated tenancy. And so if that's a concern, you need to look at VPS. You can't use the other additions. And Firebolt by default runs isolated tenancy as well. There's no shared infrastructure for the compute and the storage. It's all in an isolated tenant. So that's the first comment. Isolated tenancy, you need to think carefully about whether that matters, because that might be a key criteria. The other thing is the type of engine you need. And there are two types of, I wouldn't call them quite religions, but there are two types of beliefs. Can you have a federated query engine across multiple lakes or sources? Or do you need the engine to use its own optimized but separated store? And I kind of look at federated query engines two ways, and you might think about it this way as well. The original reason for doing it were for two reasons. One, you wanted to leave all the data in place. You didn't want multiple copies. It was hard to get it out. And you wanted to be able to do self-service analytics. Let an analyst be able to access new data sources to build new reports and do it quickly, because the business was saying, I need the report yesterday. Now, if the analyst can do it on their own, great. But you need to understand if they can or not, because in the case of Presto, for example, you need to provision the resources. Some expert needs to go in there and turn that resource into a quote unquote table, a resource that can be accessed via Presto and turn it on. That actually is not good enough for an analyst because they can't do it on their own anymore. They have to wait. So think about why you need the federated query engine. Is it to keep down the number of copies? Is it to accelerate creating a new report? What's the process that an analyst has to go through? Because honestly, pipelines have gotten good enough that you can easily suck more data out of a data lake and pipe it into a warehouse. And there you've got the performance. You not only have the new data accessible, you have the performance as well. So carefully evaluate why you need a federated engine or not. I think to give Amazon some credit, when BigQuery came out and Amazon had to respond, Athena was a good response for the standalone one-off query kind of infrastructure. And what they added with Spectrum makes Redshift users, gives them a great option, because Spectrum is dedicated compute resources for Athena within the account, within the VPC, with the Redshift VPC. That's well done. So if you're a Redshift customer and you need some one-off or external table access, I think Spectrum's a good choice. But in general, think about why you need a federated query engine, because you can't have external data access and performance at the same time. Hadoop taught us that. We've learned that from Presto. So just be aware. If the data is in a far distance, if you have to pull multiple data sources together, you can't defy the laws of physics. It's going to take a lot of time to pull that data. So it's not going to perform as well. I wanted to spend more time on a couple areas. One of them was the choice of infrastructure, but I also wanted to spend some time on the storage as well. The challenge with a separated storage and compute architecture, decoupled storage and compute architecture, it gives you a lot of flexibility, but it introduces two bottlenecks. That's the storage and the compute. Pretty simple. So I had one architect put it to me a long time ago, and it was a great line. You can't defy the laws of physics. If you're going to put storage far away, and then you're going to expect this, thin straw to be able to suck out the data fast enough for the compute to operate, you're not thinking through that very carefully, because networks are only so fast. There are some networks that are blazingly fast, but even a modern corporate backbone, a 10 gig E, can move a gigabyte a second if you're lucky, fully loaded without collisions. And we're talking terabyte level scans now. That's too long to wait for all that data to come across the network. So you have to think about, can I optimize the storage and compute architecture? Can I prefetch, move the data into local SSD cache, move it into RAM? Can I do as much of that as possible? But then when I'm fetching it remotely, can I minimize that? And the challenge is, if you look at starting with Redshift, but with remote storage, well, not really starting actually, starting with Snowflake and BigQuery and Athena, when they fetch data, they fetch partitions or micro partitions or segments. They're not fetching just the range of data they need. Pruning and all those techniques, they fetch the whole partition. That's 10 times more data than you need for the query. That means you have to wait 10 times as long for it to come through this small pipe. That's a problem. That needs to change. The second is the compute bottleneck. For those of you that have been in this business for a while, you look at how these new analytics technologies pop up. A lot of them borrow their engines from somewhere else. Under the covers, it might be a Presto. It might be, I'm trying to remember some of the other engines that I've seen, but it's, they basically borrow the query generation or the query compute layer from somewhere else. And they don't optimize it as much, and it could be Java-based. Part of the reason Firebolt was started was because Eldad, who is the founder of Sisense as well, realized that behind every good UI tool, there needed to be a great engine. And the question was, what's the engine driving this pretty picture that's going to make this pretty picture, this report, run fast? And he and the rest of the team realized there really wasn't anything out there in the data warehouse space for doing this. So the query engine that we're talking about here is completely C++ and built from the ground up as C++ and optimized in a whole bunch of ways, some of which come from high performance traditional on-premises data warehouses, and some techniques come from modern compute from the last few years. And so we'll cover those, but you need to optimize the compute. You need to optimize the storage and how you get stuff out of the storage. And you need to glue the two together really well. And that's indexing. That's one of the big things there is indexing. So we're gonna talk about that. I think if you look at the Firebolt architecture overall and pull back and look at it, it's a decoupled storage and compute architecture, right? It looks pretty much the same as what you'd see in a Snowflake. If I threw up a Snowflake diagram from the old 2016 white paper, it's going to look pretty similar. The difference is in the details. One of the first things that Firebolt realized as they were building up is when you have an engine, which is like a virtual warehouse in Snowflake or a cluster, a data warehouse cluster in other products, you should be able to choose any type of EC2 type, any balance of CPU and RAM and SSD and disk and network, because those are the things that matter when you're tuning it and you're optimizing it for a specific workload. So you should be able to do that. The engine should be optimized. That's true. You should think about indexing, and you should think about how you optimize storage. So I want to spend some more time on those. Those are the key differences when you look at this architecture, the index, the instance type you're running on, and the network bandwidth as well, and how you optimize storage and indexing. All right, so the first one is the choice of infrastructure. You should be able to choose however big, massive node you need if you have a certain type of compute that needs a lot of RAM and CPU. And here's one of the things you have to watch out for, especially with something like Snowflake. Redshift gives you choice of types. There's several different sizes and shapes of infrastructure you can choose for your nodes. In the case of Snowflake, that's not true. It's a little bit like a Ford, a Model T Ford. You can have whatever color you want as long as it's black. You can choose 1 or 2 or 4 or 8 or 16 or 32 or 64 or 128 node clusters. Every time you go up, double the nodes, double the cost, and you get a slightly bigger node size, and you don't know what that thing is. You don't know how big it is. You can only see from the query profile whether you're spilling over to disk and whether you need to go up more. And that's a problem because there are certain use cases where you can really only scale up with Snowflake, meaning a really large query where you have to do massive joins, some query complexity where you need a lot of RAM. Semi-structured data, turns out you need a lot of RAM. In those cases, you need to scale up. And unfortunately, that means you need to keep doubling and doubling and doubling until you get the right size node. A choice of instance type, the way Redshift does it and the way Firebolt does it, means you can have a cluster that's 4 massive nodes. You can go up to 100 CPUs and 400 gigs here. Whatever size you can get out of AWS, you can get into a Firebolt cluster. That helps. That helps a lot. Okay. The same with the network bandwidth. You can choose certain EC2 types that have more network bandwidth and are more IO optimized versus more compute optimized. And that matters too. Dollar for dollar, if you can make that trade-off, that makes a big difference. Let's get into speed. And it's hard to separate these. I've divided these up into architecture and performance and cost and scale. Really, you're trading off all of them. You're trading off speed, scale, and cost as you tune here. But I've broken them up a little, and I think performance is the meatiest part because the need for speed is really what broke second generation data warehouse architectures. The reason they got redesigned is because people needed second to sub-second level performance at scale, and you just couldn't get it. So what isn't different here is actually, let's go into that first. What you don't necessarily need to spend so much time on is caching. To some extent, caching is already there. Every modern decoupled compute architecture for data warehouses anyway has a local cache. You pull the data from remote storage into the local storage of the compute, which is usually SSD, and you run it from there. And it pulls it in as it needs it. It pulls it in maybe with some warming up of the cache, maybe with some prefetching algorithms, but it is a cache. There are some also that have result caches. Snowflake has a result cache, for example, where if you're running exactly the same query again and again and again, that cache is going to make a difference. But when it comes to performance, it's not repetitive queries that are the big difference. It's the first time queries, the interactive queries, the ad hoc queries where you couldn't possibly have cached that result because this is the first time you're running the query. That's why Fivetran ran their benchmark the way they did. They're testing out first time queries every time. They're clearing out the cache and running it again. And that's why we get questions when we're demoing, did you clear the cache? Because they know this is a first-time query. They want to see first-time query performance. So the caching is not as much of a differentiator. Ingestion latency might not be either, to be fair. So we'll talk about low latency ingestion. And it's a major bottleneck in data warehouses because most data warehouses were designed for batch. And they were designed for batch because in many traditional use cases, batch is good enough and latency isn't a big deal. It's more the query performance that's the big deal. So you need to evaluate whether for your use cases, you need to worry about ingestion latency or not, to be fair. It may not be as big a deal for you. Operational use cases, it can be. Customer use cases, it can be. Regular BI, maybe not so much. So think about that. What is different, though, is the storage optimization. It's a big deal. So is the compute. And so is indexing and other parts that are the glue between the storage and compute. And then there's certain types of data and use cases like semi-structured that are. So I want to spend the most time on those and talk through them in a little bit more detail. One of the big things Firebolt did was rewrite a storage layer. They call it, we call it FFF or F3. Firebolt file format. Now, it's a little bit of a lie because it's not a file. It is a segment structure. It is a sorted, compressed columnar format So it's similar to many others in that in analytics, columnar stores are really the way to go. But it's different. And it solves two big problems. And the first problem I want to talk about is how it accelerates queries. So when you load in data, Firebolt will ELT it in and write it to F3 and index it using a primary index, basically, that's called a sparse index. It tells you where the data is, where each range of data is within each segment. Okay, it's the range. It's not the full segment. A sparse index is not used as a pruning index where you decide which partition to pull over the network. It's used to access the specific range of data you need for that specific query. It reaches in, it pulls it out across the network and leaves the rest of the partition there. The local SSD cache is storing just the ranges, just the data that's being used in the query or that's been used in previous queries. Now, you can warm it up. You can come up with other ways of getting more data in advance into the cache. But the essence is it's pulling 10 times less data. That's a big deal. That's where you get your speed, or one of the places. The second is, once you start running the queries, what kinds of optimizations have you done to run the query quickly? Now, there's some optimizations that you really should expect in a query engine today, and they're not all there. So for example, vectorized processing. Batch up your data into an array, load it into the CPU, and let one CPU command run against the full array at the same time, instead of running one row at a time. CPUs work that way. You should be doing it. Only Snowflake and Firebolt do it right now. That's a problem. And you're seeing some specialized engines adding vectorized processing now, but it's not yet into the cloud data warehousing space. Just-in-time compilation, meaning do your cost-based optimization, think about the ordering of the query based on how fast you can fetch the data, where the data is. Do you want to reorder, bring filters up before you run a full query? How do you want to optimize that? Firebolt will do the cost-based optimization and the JIT, the just-in-time compilation, before it runs, and that's important. And there are other optimizations that happen here that have been shown. You ask us, where do we get this 10x improvement? Part of it is the fetch of the data. It gets you down to sub-second level just for the fetching. But then that sub-second for the query performance, that's coming from this, and that's coming from indexing. And indexes matter. We know indexes matter. We've known for decades that indexing matters. And yet, really, pruning is the most common example of indexing inside all these cloud data warehouse engines. There isn't other indexing that's really done here. You can see sorting, which is done with clustering keys, partitioning with the keys, but it's not an index. And that's a problem, because if you ask us where this 10x plus gain is coming from, one of the areas is indexing. And it's not just the sparse index. It's the actual query, the compute as well. So Firebolt has a couple different types of indexes. For the most common types of operations, namely the filter, the group bys, the joins, we've got join and aggregating indexes. Join indexes operate as basically a RAM hash table based first half of the query. It allows you to quickly, from one side of the join, match data so that you can just end up doing a bunch of lookups into the second table, which could be a fact table, to do a full join. Very fast, because it's a small index in RAM that's constantly being used for those lookups. Aggregating indexes are almost like a materialized view, in that you can store the summary, the distinct counts, you can store fact table data, the details, and resort it, and use that with the join index to do what a materialized view really should be. Both are being done as ways of offloading compute from the CPU, as taking down the amount of RAM that you need, so you can get much smaller nodes and clusters to do the same kinds of operations, and you get much faster performance. My point in saying all that is, when you look at data warehouses, you're going to look at things like materialized views. You're going to look at how you have to do sorting versus turning it on automatically in the warehouse. You're going to ask Snowflake users, for example, why don't you use clustering keys for the automatic sorting? Well, it's a huge overhead, so we just end up resorting ourselves and loading into the warehouse periodically to get better performance. You're going to have categories like materialized views, resorting, thinking about how to shrink your segment size, optimize your segment size, and compare that to things like indexing. That's all going to be part of this comparison that you need to look at when you compare and think, how am I going to get overall performance? And then you're going to run the benchmarks and think about what's really making the difference and how do I tune. That has to be done for this. And indexing is one of the things you need to look for. Okay. There's also semi-structured data. If you're not dealing with semi-structured data, you probably will. Because customer data, device data, application data, a lot of the logs that are coming out are starting to all be JSON, for example, or some semi-structured format. The problem is that you have some data warehouses like Redshift. Redshift requires you basically to load everything into tables, traditional warehouse format. You have to flatten it all. And the problem with flattening is the way we like to analyze this data, we like to go down a couple levels to match things. And that ends up being a nested query. And a nested query is the kiss of death for any data warehouse. You don't want to do it. It's better to have the data more highly structured and have a way of walking the structure. And so Firebolt lets you walk it. It allows you to do any combination of unnesting. It's an unnest command in SQL during your ELT, or doing an actual load of the JSON natively into a nested array structure, a native type within the data warehouse. So now you can write within your SQL, you can write lambda style array functions, which if you're familiar with these kinds of functions, we've gotten used to over time with JSON. And write that directly into your SQL, any combination of indexed queries across columns where you flatten some of the JSON and native JSON. With something like Firebolt and this kind of structure, it means you can have smaller nodes and faster compute, because take something like Snowflake. Snowflake, you put all the JSON into a variant column, and you have to pull all the JSON out as text, load it into RAM, and process it. That's basically how it works. That means you have to do a lot of RAM, and you have to do full scans of the JSON, which is a lot of compute. We are back to the situation of having a large node requirement inside Snowflake. And a large node requirement is not something you want in Snowflake. It's a very costly requirement because you have to go up to a huge cluster size, right? So those are really the biggest areas of performance you want to think about. Query engine optimization, the indexes, and the storage and how it works. Scalability is also somewhere you need to look. And to a large extent, scalability has been solved, right? Meaning elastic decoupled storage and compute has allowed you to scale the data and allowed you to scale the queries. But it's kind of like the meat in the middle of a sandwich. You still need to load the data in at scale, and you still need all these users to get it out. And it turns out ELT, or loading into a data warehouse, is really throttled by the batch-based architecture that most data warehouses use. It's not elastic. And the number of users you can actually throw at a data warehouse is not actually that big in many cases as well. So you have to think about end-to-end elastic scale. You need to make sure you have the two pieces of bread you can slap around the meat and have a full end-to-end elastic meal, okay? So the first thing I wanted to point out is, in order to fix elastic scale, you need to get rid of these batch-based bottlenecks. And I'll give you a few examples. Redshift, with Redshift, you have a traditional database kind of multi-master scale architecture. You have one write master, and you can make copies of the clusters to handle reads, and replication gets the data out to the copies. Turns out you can only have 15 writes queued. Sorry. It turns out in the case of Redshift, there's a certain amount you can write in because of table level locking. The tables actually lock at the table level. It's not a more detailed lock. In the case of a Snowflake, there's a limitation of 20 DML writes per table, because they have to rewrite the partitions every time the micro partitions every time they do a write. And you're going to see this across most of the data warehouses. The way around that is actually to change the columnar, the way you write to columnar stores. And Firebolt came up with something really brilliant. It's one of those, I wish I'd thought of that, because it makes perfect sense. In the case of Firebolt, you use SQL to write all your commands, and the external data is treated like a table. When you write it in, it gets written in. Any node in the cluster that's doing ELT can write a new segment that's 1 row or 1,000,000 rows. It doesn't matter how many rows. When it writes that segment in, the sparse index, remember the sparse index, just points to it. And the old segment that has the old data, it's basically not pointed to anymore. And just like Java garbage collection, the engine merges old segments together over time and compacts it so that the pointers are going to a new compressed segment, but it happens after the fact. So it's a really fast non-locking write of any, one message or a whole file, and it's immediate query visibility. It was a pretty brilliant idea, and something that you look at and you go, why didn't I think of that? Because it's pretty simple too. The other piece is user concurrency. And what I'll mention briefly, and it's hard to go through everything in a single webinar, but what I'll mention briefly is Redshift has a limit of 15 queued queries per cluster and about 50 across all clusters. It's just the way these limitations surface, whether you're locking in how you write data to tables or do queries or, query metadata. That's how it surfaces with Redshift, about 50 queued queries max. Athena is 20 queued queries. You can have 20 concurrent queries per account. Snowflake does a good job of scaling horizontally. It can be expensive. So you need to understand how these things scale. In the case of Snowflake and Firebolt, you scale by starting up more instances of the same engines or virtual warehouses or clusters, and it works pretty well with true decoupled storage and compute. But you need to think about how efficient the scaling is too, okay? And that's where this is different on the cost side. It's not that simplified administration is going to save you a lot of money across the different warehouses. They're all becoming simpler and simpler. And it's not the pricing model per se. It's the efficiency. So in the case of Firebolt, the way this works with the way the engines work and your choice of instance types, you end up choosing 10 times fewer nodes. And what we decided was we would expose all the pricing. When you choose your AWS infrastructure, you pay AWS prices. We show you what the prices are. They're the prices that AWS is charging us, and we pass it right through. So you have complete transparency over the, what you pay and how you tune for your infrastructure. And then you pay as you go. And the beauty of it is, as you tune and as you take advantage of the optimization and choosing the right types, you end up having 10 times less compute per workload, per query. And that's where you save your money. That's where you become more efficient and have a lower cost. And when you get to that level of lower cost, you can unthrottle your users. It's not like you're going to have a query that breaks the bank at this point. You have a way of controlling that. And when you can open up more resources for everybody, and then you can let the business, all the employees or the customer, go after this data and do all kinds of analytics. But you need to think about the costs and add up these costs and do the math. Do the math by use cases, so that as you're looking at each use case, maybe traditional reporting, although that's not really going to be as much of a difference in your evaluation, because they all do good. They all support reporting well. How do you support ad hoc and interactive analytics? How do you support the real-time continuous ingestion or employee or customer-facing use cases? And what's the cost? And I'll tell you something honestly. When we did the ranking in the use case section, and we said the pluses and the minuses, we didn't actually look at cost. There's no cost component to these scores. And so for each use case, as you do think about the use case, you need to calculate your own cost of ownership and a return on the project as well. And that's going to be separate. I think this is pretty much where we can leave off and open it up for questions. I'd say, hopefully, I hope you've gotten a sense of how you might use this, all the requirements. You can read through the comparison guide and pick the ones that matter for you. I would do it after you've identified your key use cases, because your use cases are going to drive your criteria, and then lay them out, put down your combined use cases and score and weight them as you see fit, and then use them to drive your POCs and your benchmark as well. All right. With that, I think we have some time for questions. Although I think, Tamar, you also wanted to do another ask a question yourself.
Yes. So one quick poll before we move to questions. Would you like to check out Firebolt?
I can't vote, right?
So basically you only have two options, two like legitimate options after this presentation. Okay, thank you. We will reach out to everyone who responded. Now, as Robert promised, I'll just post in the group chat our giveaway. Like a giveaway, don't get too excited. We're not Oprah, but it's still a useful asset. Let's post it here. And we can move back to the questions.
All right.
Okay. So first question, Robert, how does Firebolt handle semi-structured data versus Snowflake?
Okay, we covered that a little bit, but basically Snowflake can process semi-structured data. It doesn't store it natively. It stores it as basically a long text string, not quite as a blob, but just as raw text. So Snowflake needs to pull it out, load all the text into RAM. So if it has 1 million rows, 1 million versions of that text, and then just do full scans across that text to pull out each field that it needs for its compute. And that requires a lot of RAM. It requires a lot of compute, which means a big node. And the last thing you want in Snowflake is a big node requirement. In Firebolt, we structure the data, the JSON natively. You can choose whether to flatten it or structure it. You can do both, but whatever's structured is stored as a nested array type. And within SQL, you can do nested array functions. So you don't need the full scans. You don't need a lot of RAM, and it's optimized to walk those structures. So it ends up being pretty fast. And it's one of the reasons why people look at us for semi-structured data use cases.
Okay, next question here. How is Firebolt better than Athena?
Athena is Presto. It's a commercialized version of Presto. I know there's a lot of debate about that, but that's basically what it is, with some features around it that make it simpler. And Athena is a shared resource. So the first thing is, if you're worried about isolated tenancy, you can't really use Athena. Athena is great for one-off queries or occasional queries because it's priced at $5 a terabyte. And so if that's what you need, it's a great option. If you're a Redshift user and you need something like Athena, you should be using Redshift Spectrum because it's dedicated compute within your cluster. And it's a pretty good deal, actually. So I'd recommend, if you're using Redshift, do it that way. But there's a big difference between a federated query engine that has to pull data from multiple places remotely, which is usually a lot of data because there's a little bit of push down, but usually you're pulling massive data sets and then you're doing your compute against them. So it's going to be slow. If you need any kind of performance, you need to pull the data in before you do the query and then optimize the storage and then optimize the query. And that's what Firebolt does. That's really what Redshift and Snowflake do as well. Optimized query engines optimize with their storage, and Presto isn't.
Well, we have many more questions, but our solution architects tried to answer as many of them live, and if not, then we'll respond. We ran out of time, but thank you everyone for joining, and thank you, Rob.
Yeah, if people have any questions or more criteria, you can always email me because this is a living document, just like what the guys at Fivetran are doing with their benchmarks. There's always room for improvement, and feel free to add comments on where it could improve. Go follow us on LinkedIn or find a way to follow us. We'll be posting other things. I think we need to do more around benchmarking, so we'll probably talk more about that. And we're going to deep dive into various other data warehouses, not just all of them at once. So feel free to follow and look for the next conversation. And maybe you have a great idea for what we should be covering, so feel free to reach out.